In this session, we are going to have a detailed discussion regarding the stationary and time series. We're going to use the Finance Research Guide website as we usually do, but first let's really grasp the underlying theory. What exactly does stationarity mean in this context? Essentially, stationarity implies a state of stability.
Stationarity implies that we must observe three key characteristics within any given time series.
We are observing a situation where the mean value remains constant and its statistical variance also stays constant. And for the autoregressive component, the statistical relationship of the current value with its previous observations at a specific time lag is required to be maintained at a predetermined constant level. This doesn't mean that for any given lag difference, we're going to find the exact same value. Instead, at a particular lag, let's say lag 1 or 2, the covariance itself should then remain stable and consistent over time. Stationarity means that the underlying process of a time series variable maintains stable characteristics, such as a constant mean and variance over time. For example,
here we have plenty of time available.
And here we have the significant variable.
and so the numerical value itself is constantly moving up and down, fluctuating significantly based on the specific variable that we are currently discussing in our analysis. Stationarity implies that the statistical properties of a process remain constant over time. This means that the distribution of observations depends solely on the time interval between them rather than their absolute position in time or space. So, if you consider a specific duration or a particular time period, a specific interval of time at this particular location when compared to an identical interval of time at a different location, the overall distribution of events should be precisely the same. This is a rather significant stationarity assumption to make, but in this particular context, the underlying distribution actually possesses a great many variables that we must carefully take into account. Therefore, our analysis will primarily concentrate on three fundamental aspects, with the most important being the mean. We also direct our focus to the variance, and also the statistical measure known as autocorrelation. It is essential that all of these specific parameters maintain a consistent value throughout the entire duration. Now, if these particular measured variables, our fundamental understanding of how things do change over time, meaning that the very location of time itself will inevitably change in these specific circumstances.
If there are variables present within the distribution, it means that we do not have stationarity.
So let's take a moment here to have a truly comprehensive and thorough discussion about all the different types of non-stationarity that we might encounter and, crucially, how we can effectively approach and solve each one of these specific challenges. We'll begin by addressing the very first one. The first type of non-stationarity that we need to consider is the stochastic variety. The second type, in clear contrast, is defined by deterministic non-stationarity itself, and the final category, as you might expect, is simply a mixture or a combination of these two fundamental types. The stochastic non-stationarity is also commonly referred to as the unit root. For instance, if we are considering a specific model for a particular variable, and we then perform a regression of that variable on its previous value, which is denoted as xt minus 1, in such a case, the outcome we obtain is what we call the raw coefficient. If that raw coefficient equals 1, it means we have a non-stationarity. This error is caused by the continuous accumulation of individual errors over an extended period of time. Consequently, any individual error or sudden shock introduced into the system will not dissipate but will instead persist indefinitely. Therefore, we should now investigate how this specific characteristic is clearly demonstrated within the mathematical framework. Therefore, we are able to substitute the variable x at a time t minus 1 with this particular expression, given that it represents an autoregressive process. Consequently, this quantity becomes equivalent to we are considering the variable x at time t minus 2, and then we add to that the error term that is lagged. If you're able to substitute this particular term right here, and as a direct consequence, we will then establish this crucial relationship. This means that the variable xt will ultimately be expressed as a function of xt minus 2, which represents the previous lag error and also the current error that we are observing. Similarly, we can substitute this particular element with its component parts. Specifically, that would be the xt minus 3 term and also the u, or perhaps the error term t minus 2. And if you were to plot that out here, then we would end up with exactly the same variable.
But at this point, there are more autoregressive sections involved.
We can perform this decomposition process on this variable x, specifically the lagged version of x, continuing until we arrive at the very first x term, which is commonly referred to as x0, representing the initial x value. And in the course of this analytical process, we will be creating a substantial number of lagged error terms. For instance, we'll have t minus 4 and over similar temporal displacements and so on. This specific concept is what we refer to as the term in our discussion. So, it's important to understand that the errors will progressively accumulate and become quite significant when the coefficient value here is exactly 1. If the correlation that we observe here, if the raw relationship or coefficient is less than 1, then it implies that the errors will eventually disappear and will never be accumulated for such an extended duration.
Does that actually create a problem when analyzing a variable? The answer is yes, because if you have a shock event that occurred, for instance, 100 years ago,
this will be a significant factor in the level variable for today, and consequently, it will make it much more challenging for us to accurately forecast or effectively run regression because the underlying relationship is not stable over time. So, why exactly is it that this particular process or series is considered non-stationary? Again, the primary reason for this classification becomes clear when we carefully take the expected value of this specific decomposed component or term. Then we are left with x0, and then we add the expected value of the error term. By definition, the expected value of the error term is precisely 0. This is fundamentally because the error itself inherently possesses a 0 expected value. In other words, its mean expected value is always equal to 0. Consequently, we then derive an expected value of x that is also 0. So, the mean value remains constant, which perfectly aligns with the initial condition that we had mentioned earlier. The mean is indeed constant. However, the variance, on the other hand, does not remain constant. If we take the variance of xt, we then have the variance of x0, which is a constant value, and because of that, we don't have a variance for a constant, it is 0. But then we have to consider the variance of this total accumulated error, and this variance itself would be accumulated across all of the individual errors, precisely because they are entirely independent. So the rule here is that if you want to find the variance of a variable that is independent over time, it would be simply the sum of the variances of each term. So we'll be adding up the variance values from various preceding time steps like t minus 4, t minus 5, t minus 3, and so forth. Consequently, the total sum of these variances would then be equivalent to t multiplied by sigma squared. Meaning that as time advances, as the progression of time continues, the errors will persistently grow and multiply without end, approaching infinity, should the variable t itself be infinite. Consequently, the variance of this process is not bounded, and it continuously increases without any upper limit. This directly implies that the process xt exhibits non-stationarity. How can we effectively tackle this particular problem? In most situations, applying the first difference is usually all that's required to achieve our objective. For instance, let's clearly define what we mean by the first difference when we're looking at a variable xt. Specifically, this is calculated by taking the current observation xt and subtracting the preceding observation xt minus 1. Let's take a look at equation number 4, and if I can just direct your attention back to equation number 4, the one we were just examining, you'll notice that the resulting difference in this context is simply going to be represented by this specific term, which we've labeled as xt. So we're substituting the component of xt, which is the lag xt, and the current error. If we subtract xt from this mathematical equation and then proceed to perform the necessary calculations, what remains is simply the error term. Therefore, applying the first difference operation will effectively eliminate the lag component, or more precisely, the autoregressive element. And that specific value will be equivalent to u plus an additional error term. It's important to remember that the correlation we're discussing here, or the raw coefficient, is exactly 1. This fundamental fact explains why the xt minus 1 term will be eliminated from our equation. Consequently, the xt term itself will essentially be removed. What remains, the sole discrepancy, is simply the error term. So, if we are considering this particular difference series variable, the question is, does it exhibit stationarity? To determine this, we should proceed by calculating its expected value. The expected value of this particular variable is 0, which means that it remains constant. And for the variance of the error term, given that we are only dealing with a single error term in our model, it logically implies that we will only have one variance term. And the covariance between the current value and its lagged value of this newly transformed series, which has been put into its difference form, is going to be a direct function of the covariance of the current error term with the immediately preceding error term. Because if you are looking to calculate the lag of the difference to x, then that would certainly be the correct answer. So what exactly is the covariance between the lagging error and the current error? In this specific case, that would be much easier to understand since we don't have serial correlation in the error term, which means it would be 0. So this clearly illustrates a random walk. It's important to understand that it can also incorporate a drift component, which will be the primary subject of our next discussion.
Let's look at this with the very same idea. The raw coefficient in this particular instance is exactly equal to 1, and we also have the inclusion of a constant term. So what do you think the ultimate outcome will be in this specific case? We can certainly work this out through a detailed derivation process. This is our xt variable.
This particular variable is expressed as a function of the preceding value, xt minus 1, along with a constant term and the error component, ut. Then we can return to the original source, which is the very first x variable. How do we achieve this? We simply perform a substitution right here. But to consider the individual components that constitute xt minus 1. This value, xt minus 1, is then equivalent to xt minus 2, which is the lagged version of the original series. Additionally, we have the constant c, because this c value is present in every single x variable, whether it's x at time t, x at t minus 1, x at t minus 2, or even x at t minus k for any k. This constant c will consistently be present along with the error term at t minus 1. So, if you were to take this component and then connect it right here, you'll clearly notice that the letter C will appear more than just a single time, both in this specific spot and also over here. And if we continue to decompose the xt variable down to its individual lag level, then we are also going to have an additional constant term C. And of course, just as we observed in the previous case, we will also encounter another error term. Therefore, we're not just going to accumulate the errors in this situation, but we're also going to accumulate the C, which represents the constant term. So this is the final equation for xt that follows non-stationarity. Let's consider the expected value here. The expected value of this particular component, we find that it is precisely 0. It represents x0, which is the very first x value within our given time series data, and to that we add the old accumulative c terms, which are essentially c multiplied by t. So the duration for which you choose to analyze this particular variable is quite important. For instance, if you're looking at a period of 10 years, then you'll end up with 10 distinct components contributing to this constant term. However, if you extend that to a full century, you'll then have 100 instances of this.
Though, in this particular case, the mean value is not remaining constant, and the reason for this is quite clear. It fundamentally depends on the variable t, which represents time. Therefore, as time progresses and becomes longer, we observe that the mean value itself is continuously changing.
It might be growing if the constant c is positive, or it could be declining if c is negative. Plot pause. Whenever the time series itself is a direct function of time, we then lose the property of stationarity. The variance is also not stationary, because if you take the variance of this equation, we know these are constant, so they will be 0. This error term is not constant, it has a specific value, and because we have too many error terms, we then multiply by t. So, if you're considering 5 distinct periods, then you will have 5 separate error terms. You must multiply the variance of each error term, which is represented by sigma squared, by 5, and continue in that manner.
But if we were to consider taking the first difference of this data, yes, that is certainly an option available to us, and we should investigate whether this approach effectively resolves the problem we're facing. Once we have successfully applied this first difference operation, it then becomes possible for us to replace the original xt variable with its corresponding lagged value, along with the constant term and the associated error term in our model.
Of course, that particular component will cancel out with this one, and we'll then be left with just the constant term and the associated error term. Now let's proceed to take the expected value of this expression. The expected value of the error term itself is 0, and the constant term will simply remain as a constant value.
It is important to note that the variance of this particular difference time series is equal to the variance of c combined with the variance of ut. The variance of c is 0, as the variance of a constant value is always 0. The variance of the error term, however, is simply sigma. And since we only have a single error term that appears in this equation, we consequently only have one error term, which is sigma. The covariance between the variable x's difference and its corresponding lagged difference will inherently take on this specific mathematical form. Given that the constant involved appears consistently as a single unchanging value across the entire observed time period, we consequently do not find a covariance of 0 in this particular instance. Therefore, this particular aspect can be disregarded. What we are left with is the error term, specifically its covariance component. Because there is no serial correlation present within the error term itself, its value will then become precisely 0. See, for example, in this particular scenario, if we are considering a model that possesses both a drift component and a unit root, we then commonly designate it as a random walk. We are unsure if this represents the true xt value or if it's merely the accumulation of error from the initial x0 as time progresses. And it's also quite possible that this particular trend is being caused by the addition of a constant value over time. Therefore, it's clear that nothing is directly related to the actual level of xt. Instead, it's merely a function of those accumulated errors that unfortunately never truly disappear, along with the persistent accumulation of a constant term.
And that will give you a spurious or false relationship if you try to relate the xt with another variable. What you are seeing here is not actually the true xt, it's simply the errors that have accumulated along with an accumulated constant term.
The second type, which we're discussing, is fundamentally deterministic. In this particular case, we clearly observe a trend, which essentially means that the specific time period will directly affect the resulting value of xt. However, in the previous situation, we specifically utilize the lag, which represents the autoregressive component or part of xt.
Here, the situation is quite different. In this context, we are now employing the time period itself as our independent x variable. And this particular phenomenon is what we refer to as the deterministic trend. This approach consequently will inevitably lead to a non-stationary situation.
Why? The fundamental reason is that if you consider the expected value, then you will ultimately be left with a constant value, which is then combined with the coefficient b that has been multiplied by the specific duration of the time period. It's essentially like running a regression of x on a specific time period. And just like in any standard regression analysis, we will certainly have a constant term, and we are also going to have the beta, which, as you know, is the coefficient that's attached to our x variable. And in this particular scenario, that x variable represents the time period.
So that would be the expected value.
Now, since the mean value is not constant, it changes and is dependent on t. Consequently, the primary requirement for a univariate time series variable, which is to maintain a constant mean over time, will not be satisfied. In this particular instance, we can clearly see that xt is not a stationary process. It's important to carefully observe that we do not experience any accumulation of error. Instead, what occurs is simply that the expected value itself varies and changes over time.
How can we solve this issue? We can implement a technique called detrending, which means we'll remove the trending factor from the xt data.
This process is what we refer to as detrending. And yes, by doing this, we will effectively create a stationary variable. This means that, once again, we won't have an error term that accumulates or builds up over time. Instead, it's simply the passage of time itself that will determine the expected level of our xt variable. If we were to carefully remove the underlying trend effect, which we can identify as this specific component from our initial xt variable, then the resulting yt variable would then simply represent a direct function of the inherent error once we have successfully eliminated that persistent trending behavior. And because the yt, which represents the error term, is considered stationary by our initial assumption, it follows that the new series we've created, specifically the detrended series derived from x, is also stationary. In essence, what we're doing is simply removing the underlying trend effect. So the variable x is no longer acting as a direct function of t, and now we no longer have the original x. Instead, we're using a new variable. This new variable is precisely what we refer to as the detrended variable. Because we don't have t acting as a significant factor here, it is therefore considered stationary. In some cases, you might even find yourself facing a more intricate mixed situation, where a specific trend is impacting the x, and also these errors tend to accumulate and never truly dissipate. This is a unit root effect. So in this particular scenario, the variable z, which we're looking at here, actually represents the autoregressive component of the error term within our model. This specific error term, as you might expect, could potentially include a constant value, much like the c we've encountered previously in other equations. Furthermore, we also need to consider the inclusion of the variable t in our analysis. So, we're considering three important aspects here: the accumulated constant, the accumulated errors, and the overall trend effect. Should you proceed to calculate the expected value of that particular element, you will then discover the presence of the trend effect along with z0, which, as you may recall, bears a strong resemblance to the constant c that was presented in our earlier example. It clearly depends on t, so our first condition simply fails to be met. The variance will also fail, primarily because of the accumulated error present here, and since this is a function of t, it cannot remain constant.
Should you choose to apply the first difference method, you'll inevitably find yourself dealing with these particular terms. When you take the first difference, you'll be left with just a coefficient, or the impact from t, which we often refer to as beta, for example, along with the other remaining term. If you then take the expected value of that, you'll ultimately be left with only the coefficient.
The variance would be the variance of b, which is a constant value, so that would then be 0. Here, that would be considered a constant term because you only have one other term present. Considering the covariance between the first difference and the lagged first difference, we will simply ignore this specific part because it is a constant, and we are assuming that there is no serial correlation of the error term. So the first difference also will solve the problem here. If you have both a deterministic trend an accumulation of lag errors, or even constant term, a unit root, which is also referred to as a unit root problem.
So let's proceed to apply these fundamental concepts utilizing the powerful time series function as integrated within the Finance ResearchGate website platform.
Let's process the data on a monthly basis beginning in the year 2000 and concluding in 2010. However, you are free to choose an alternative sampling period if that suits your needs, and then we will proceed with the application.
Let's go ahead and select the specific variable that is identified as soybean, which for our purposes represents the current market price level of the actual soybean commodity.
Alright, so what we're looking at on this display is the current value quoted in US dollars per metric ton. This figure specifically indicates the market price for the essential soybean. It's a critically important agricultural product with major global impact.
And then subsequently, we proceed to apply our chosen filters. It's crucial to understand that we are specifically dealing with a macroeconomic indicator, which implies that we have a particular variable that holds a unique value for each and every time period.
Therefore, it makes no difference whether we choose to analyze a single company, an entire industry sector, or even the complete market. The resulting time series data will consistently exhibit the same characteristics because this particular measure represents a broad macroeconomic index and is distinctly not designed as an indicator at the individual firm level. It is certainly not a variable specific to any single company.
So it doesn't matter if you select a few tickers here or leave it empty, it will be the same.
If you take a moment to scroll further down this particular display, you will then be able to clearly observe the current price level. As one would naturally anticipate, the overall price level is not static. It is constantly shifting and evolving over time. So why exactly is this phenomenon occurring? This is primarily due to the presence of inflation within the economy, which inherently places a considerable and persistent upward pressure on the general price level.
So, for instance, we can clearly observe an underlying trend. However, the degree of variability itself might not always be constant. For example, if you carefully examine this particular time period, you'll notice the variability is considerably smaller than what we're seeing over here.
So the variance in our data is not stable, which presents a challenge. Furthermore, we've identified that there's also a noticeable trend present. Given these issues, what steps can we take to address them effectively? Our initial approach would be to apply a specific statistical test, and for this particular situation, we actually have two distinct tests available.
The augmented Dickey-Fuller, the Fuller test, and the Philip-Perrin test are what we'll cover. I'll now proceed to discuss each of these important statistical tests in much greater detail right here.
The proposed statistical test will involve regressing the first difference of the time series variable using its own lagged value as a primary explanatory factor.
A specific measured value or level of the variable x, while simultaneously accounting for the underlying temporal trend and additionally making allowances for a fixed, non-varying constant term, and moreover by incorporating the effects of previous period differences or lagged terms. Our primary assumption, the central idea we're testing, is found right here, specifically within the gamma coefficient.
The fundamental concept we're discussing here is quite simple to understand. Essentially, the y variable represents the difference between xt and xt minus 1.
If this particular quantity or measurement begins to rise, then from a logical standpoint, we would naturally conclude that it is bound to eventually come back down again.
Why is that the case? Because the xt value here is increasing its magnitude and it also possesses a negative sign. This combination will then cause a substantial reduction in the calculated first difference.
If that particular situation does not occur, then our analysis indicates the presence of a unit root, which means the observed difference in this specific case is simply due to the influence of the other term, and the xt component is gradually diminishing and eventually fading away. Remember when we were working on the deviation calculation and how each previous value was essentially a direct function of the error that occurred? So if the xt value doesn't actually reduce or go down as we anticipate,
the difference means we have a unit root that is simply a function of the accumulated errors. However, if the variable xt, specifically the first order lagged value, xt minus 1, is truly effective in its operation and does not depend on any previously accumulated errors, then we can confidently anticipate a very substantial and meaningful reduction in this particular area.
So in the event that the coefficient for gamma turns out to be exactly 0, this implies the presence of a characteristic known as a unit root within our model, and as a direct consequence, this implies that the underlying process is inherently non-stationary.
However, if this particular value turns out to be significantly negative, it implies that we are dealing with a truly stationary condition. There's another test which is called the Philip-Perrin test. The fundamental idea behind it is the same.
We are currently performing a regression analysis on the observed differences at the previous or lagged level, and the subsequent statistical testing of the resulting coefficient reveals it to be both highly significant and clearly negative. However, if these crucial conditions are not met, then we would unfortunately encounter a significant problem with stationarity.
But the crucial difference here is that the PP, which stands for Philip and Perron, is notably robust to issues of serial correlation and heteroscedasticity, specifically by incorporating the long-run variance in its calculation.
This is for the correction, so it becomes much more robust, especially with smaller samples.
So let me just go back to that.
So the augmented Dickey-Fuller statistic for our variable is negative, which is the gamma, representing the expected value. But is the corresponding p-value statistically significant? Unfortunately, it is not, because the p-value we obtained is quite large.
So, based on our analysis, we are unable to reject the null hypothesis, which clearly states that the underlying data follows a non-stationary process. The Philip-Perron test also provides the very same conclusion.
The p-value is not negative, so the negative coefficient observed here is not statistically significant, indicating that we follow the null hypothesis
That our time series exhibits a significant degree of non-stationarity, and we were able to confidently arrive at this particular conclusion through a thorough visual inspection.
So, as we've previously discussed, the initial difference proves to be a highly effective way to solve this problem, allowing us to then derive a brand new series from this point. And then we'll move on to discussing the various methods of time series transforms.
And it has completely changed the name.
At this point, we have access to a specialized detrending function, but it's often the case that simply calculating the first difference is entirely sufficient. So the initial difference would be applied, and then we would proceed to create the resulting series.
Let's just take a moment to go back, and then I'd like to present the differenced series of the soybean price. You'll notice that the variability we're observing in this data is now quite consistent, maintaining an almost similar pattern across the entire time period. Furthermore, we can clearly see there's no discernible upward or downward trend, indicating that the average value remains independent of the specific time period.
We can clearly see the significant difference. Now, if you would just scroll down to the very next section.
The observed difference in this particular case is quite variable. The augmented Dickey-Fuller test result is negative, and it is considered statistically significant given that the p-value is extremely small. Similarly, when we conducted the Philip-Perron test, its outcome was indeed negative, and it proved to be statistically significant, which clearly indicates that we now possess a stationary series. So, that concludes our presentation for today. I want to thank you all very much for your kind attention and for listening.